Hello, and welcome to the last part of our chapter on stars. In part 4 of this video, we will be looking at some of the most mysterious and fascinating objects in the entire universe. That is, neutron stars and black holes. This chapter could also be called Gravity Always Wins, because this chapter is about gravity's ultimate conquest over matter to form these exotic objects called a neutron star or a black hole. We learned in the last part of this video that the mass of a star when it's born determines how it will live and ultimately die. So for small stars, just to review, stars smaller than about 8 times the mass of our sun, they will shrink down and eventually become a white dwarf. For medium-sized stars, stars around 8 to 20 times the mass of our sun, they explode in a fantastic explosion called a supernova, and then what's left is a neutron star, and that's one of the things we are going to discuss in this video. For the largest stars, stars greater than around 20 times the mass of our sun, they also blow themselves up in a supernova explosion, but they shrink down. What's left of the star shrinks down and basically disappears from space itself, leaving behind one of the most exotic and fascinating objects, which is called a black hole. Let's start by talking about how neutron stars are formed. So remember from the last part of this lecture that we learned when massive stars get towards the end of their life, they create a sequence of shells of heavier and heavier elements as we go farther and farther into the core of the star. And these shells are all produced by nuclear fusion of lighter elements into heavier elements. And this goes all the way until we get to iron in the core of the star. So this iron core then is the last, sort of like the last straw for the star. The star can't get any more energy out of this iron core. So that means the star is not able to fight off the force of gravity once the core becomes iron. So what happens here is this iron core, which can weigh as much as 3 times the mass of our own sun, will collapse and basically implodes, all right? It explodes inward due to the force of gravity, and this all happens in a fraction of a second. And then it recoils, and the outer layers of the star are basically blown outward in a violent explosion. And this is the supernova explosion. But what we're going to focus on now is what happens to this core inside. Well, the core actually survives, amazingly. It's the rest of the star that explodes outward. But the iron core, when it's squeezed down to, a relatively small size compared to how big it used to be, all of the iron nuclei, which, remember, a nucleus of an atom contains protons and neutrons. So we end up with this, or the nuclei basically dissociates. There's so much pressure and high temperature in here that the nucleus can't remain intact anymore. So it sort of comes apart into this dense soup of protons and neutrons, and then remember, for every proton there's an electron also in these iron atoms here. So we have this this dense ball of protons, neutrons, and electrons. But what happens next is, because everything in this sphere here is compressed and pushed together so closely, the protons and electrons are forced together, and a proton and an electron can be forced together to form a neutron. So all of the P's and E's in here, the protons and the electrons, they all become N's. So what we end up with is a giant ball of neutrons, something about roughly 6 miles in diameter. And this is called a neutron star for this reason. So what is this thing called a neutron star? Well, we mentioned that typically the size is on the order of 10 kilometers or 6 miles in diameter. So it's roughly the size of a large city, the downtown area of San Diego or something like that. the mass of the neutron star is in between these limits here. It's about 1.4 up to 3 times the mass of the sun. So think about that. You have the mass of 3 suns crammed into a ball the size of a city. All right, and so remember, our sun has the mass of 300,000 Earths. So we're talking about potentially millions of Earths all crammed into something as small as a city. So how many neutrons would there be in this object? Well, the estimate is 10 to the 57 power. So that's a 1 with 57 zeros after it. You can sort of think of this neutron star as a giant nucleus of a giant atom. And so typically nuclei have up to maybe a few hundred neutrons inside of them. Well, this thing has 10 to the 57 neutrons, right? A 1 with 57 zeros after it. Now, the density of a neutron star is just unimaginably dense. It's somewhere on the order of 10 to the 14th grams per cubic centimeter. That's 100 trillion grams per cubic centimeter. So let's think about what that really means. If you had a piece of a neutron star the size of a sugar cube, it would have the mass of around 100 million tons. So that's about equivalent to all of the cars in California. All right, so you take all the cars in the state of California and crunch them down so they fit inside of a sugar cube, and that's what neutron star material is like. This is some exotic material. It's not like anything here on Earth that we can ever, even imagine trying to assemble or simulate here on Earth. The gravitational field is so strong because we have so much mass in such a small area that the gravity, remember here on Earth, what we are experiencing right now is 1g. Well, on a neutron star, the surface of a neutron star, the gravity is about 190 billion g's. So with that much gravity, all right, the gravity is 190 billion times stronger than it is on Earth. Any atoms, for example, from our body that would be on the surface of this neutron star would immediately be crushed. Basically, the atom itself would disassemble into protons, neutrons, and electrons. So in other words, it would not be a very pleasant experience to visit and land on the surface of a neutron star. Oh, also, if that weren't bad enough, the surface temperature of a neutron star is typically on the order of 1,000,000 degrees, so they are extremely hot. So what do these things look like? Well, neutron stars, because they're so small, we can't really get a picture of one in any detail, but they do give off X-rays because they are so hot. So an object that has a temperature of 1,000,000 degrees will be a very good X-ray emitter. And so this is an X-ray telescope image of a neutron star. So this bright central region here is basically the neutron star giving off X-rays. One of the other fascinating things about neutron stars is how fast they can rotate. The reason they rotate fast is because when a star shrinks down, it has to rotate faster in order to conserve angular momentum. Now, this is something we didn't really discuss or talk about in this course, but you've probably seen a figure skater when they do their spin, they start with their arms out and maybe even one leg out, spinning slowly like this, and then when they bring their arms and their leg in, they start spinning faster and faster and faster. And this is because they are actually obeying the physics law of conservation of angular momentum. So a neutron star does the same thing. When a star, which is rotating, or our sun, for example, is rotating about once a month, when it shrinks down to the size of a neutron star, remember a neutron star is only about the size of a city. So we're talking about shrinking down by millions of times its original size. Therefore, it has to spin very, very fast. So neutron stars can spin up to hundreds of times per second. And that's pretty amazing because we're talking about an object that has something like 3 times the mass of our sun and the size of a city that's spinning hundreds of times per second. This is a picture of a supernova remnant that we actually talked about in the last part of this lecture, and it's called the Crab Nebula. And inside the center of this Crab Nebula is what's remaining, and this is the neutron star. This is the neutron star, again, seen in X-ray. So this is from an X-ray telescope, and you can see the central neutron star right here, and also you can see a disk of material that's orbiting around this dense neutron star, and you can also see some jets of material shooting out from the neutron star, which we'll talk about shortly. Some neutron stars are called pulsars, and a pulsar is a rotating neutron star that has jets of radiation that shoot out from the neutron star. And because it's rotating, this thing sort of acts like a lighthouse beacon. And if one of these jets just so happens to be oriented such that it's aimed toward Earth whenever it turns around, we will see a flash of radiation, or a pulse. And so this is why originally they called them pulsars, for pulsating star. It's really a pulsing neutron star. And remember, these pulses can be happening very fast. We can see sometimes 10 or even hundreds of rotations or pulses per second. Let's now turn to the other topic of this lecture, which is black holes. Well, when a neutron star forms, it turns out that the maximum size a neutron star can have is about 3 times the mass of our sun. What happens is if a neutron star had more mass than 3 suns, the gravity would become so strong inside that neutron star that the gravity would crush it down, and that there is no force in the universe strong enough to fight off this gravity. So, for example, if the core of the star had a mass of 5 suns, or maybe 10 suns, what would happen? Well, it wouldn't end up as a neutron star. This thing would just keep shrinking and shrinking and shrinking, and the smaller it gets, the stronger the gravity gets. So it's just a runaway process, and gravity will cause it to collapse into a single point called a singularity that has no volume and infinite density. This is what is a black hole. So basically what happens here is the core of the star, which, remember, we can be talking about something that has 10 times the mass of the sun. This object shrinks down until it basically disappears. And it doesn't shrink until it gets very small. It goes to the point where it's smaller than an atom, smaller than a nucleus, and then in theory, it basically shrinks down to nothing until it has 0 volume. However, it doesn't disappear per se from space because it still has all of its mass. All it's lost is its size. And so this is, something that's very strange to think about. How can something that has the mass of millions of planet Earth, right? We're talking about taking millions of Earths and squeezing it down until it actually disappears. It has 0 size, but all the mass and all the gravity remains. So it's sort of like a place where the star was. And this is the beginning of our exploration into what is a black hole. In order to understand some of the amazing properties of black holes, it helps to understand the concept of escape velocity. So escape velocity is the speed required for a projectile to escape from a body's gravitational field. So for example, on Earth, if you take a ball or a rock and throw it up in the air, well, it comes and it stops and then it falls back down, of course, because of gravity. Now, if you were able to throw it up faster, right, with a faster speed, it would go higher but still come back down. Well, on Earth, if you could throw an object without wind resistance, let's say, with a speed of about 11 kilometers per second, which translates to something like 25,000 miles per hour, right? If you could launch or project an object, it will actually keep going up and it won't come back. It has exceeded the escape velocity of the Earth's gravitational field. All right, so that's the concept of escape velocity. On the moon, because there's less gravity, the escape velocity is much less. It's about 6 times less. On a neutron star, the escape velocity is very high. It's about 100,000 kilometers per second. But this is still less than the speed of light, so light can escape a neutron star's surface. However, for a black hole, the escape velocity is greater than 300,000 kilometers per second, which is the speed of light. So that means on a black hole, light cannot escape. It's not going fast enough to escape from the black hole. So remember that light represents the fastest that anything can travel. So nothing can escape from a black hole, not even light. Light would try to get out and it would basically curve back on itself and come back into the black hole. This is why they're called black holes. They cannot give off any light. It's impossible for light to escape from them. So they are completely dark. The next concept that we need to understand in order to learn something more about black holes is the concept of the event horizon. So the event horizon is a boundary around the black hole inside of which the escape velocity exceeds the speed of light. So what do we mean by this? Well, remember a black hole, we can think of it as this little point right here called the singularity. That's where the star was. That's where all the mass basically disappeared into this, little point right here, this location. Well, remember that the escape velocity near the black hole is greater than the speed of light. So any light nearby here can't get out. It would just bend and come back in. But once you get far enough away from the black hole, all of a sudden the escape velocity is equal to the speed of light or less than the speed of light. So if you're out here, technically you could escape from the black hole. For example, light can escape from the black hole out here, but not in here. So this sort of imaginary boundary around the black hole, it's actually a sphere, is called the event horizon. And usually we think of the event horizon as the surface of the black hole. So the black hole, even though the mass is all down here in the singularity, which has no size, this event horizon sort of defines the surface of the black hole, because the surface right here represents a surface where nothing can escape once it goes inside of the event horizon. So you can, in other words, you can check in, but you can't check out. All right, once you get inside the event horizon, you're trapped forever. You're doomed. And we have no way of finding out what's happening inside the event horizon because no information, no light, nothing can get outside of the event horizon. Things can only go in. So a typical black hole that formed from a star, these are called stellar mass black holes, have event horizons with diameters of maybe a few tens of miles, something like that. But we'll learn about in a later chapter on galaxies that there are supermassive black holes in galactic centers, and their event horizons can actually be much, much larger. They can be millions or even billions of miles in diameter. By the way, we're not going to talk about it in detail in this course, but this radius here of the event horizon is called the Schwarzschild radius. That's what the R is for radius and the S is for Schwarzschild, the physicist who worked on some of the early physics and theory of black holes. So now we're at a stage where we can sort of make a sketch of a typical black hole. And this is important because this gives us sort of a simple model and a way to envision what a black hole is. So in the center here, that little dot there, that's the singularity. That contains a mass of at least 3 suns, and it can be more than 1 billion suns for supermassive black holes, which we'll talk about in the next chapter. But that's where all the mass is, and that's where the gravity from the black hole comes from the singularity. Around the singularity is this sphere or region called the event horizon. That's the surface where the escape velocity is equal to the speed of light. And basically we think of this black sphere here as the surface of the black hole, because anything that goes inside of this surface is gone forever. Now, how do we possibly detect or prove that black holes exist if they they don't give off any light, so we can't technically see them. Well, what we can see is around the black hole, there is usually a disk of infalling matter, and this is called an accretion disk because matter is accreting here and falling and orbiting and spinning into the black hole. So this infalling matter is superheated because of the tremendous gravitational attraction of the black hole. So as this gas and dust or whatever is getting sucked into the black hole, as it's spinning around and orbiting, to its doom, basically, it gets heated up to millions of degrees, and it can be observed in X-rays. So a black hole will give off X-rays from the regions just around and outside of the black hole. Remember, nothing comes out of the black hole itself, but this accretion disk here is very visible. Black holes also often produce jets, and these are called bipolar jets. One shoots out the top and one shoots out the bottom. And the mechanism of these jets is still being researched, but it has something to do with the amount of magnetic fields and all the energy due to the gravity that sort of swirls particles and accelerates them and shoots them out almost at the speed of light from either axis of a black hole's rotation. So this is how you can make a quick and simple sketch of a black hole. This is pretty much all there is to them. Let's take a look at some of the other fascinating properties and characteristics of black holes. Some of these are predicted from Einstein's theory of general relativity. Remember that Einstein, his theory of gravity said that gravity is due to the curvature of space and time. So with a black hole, the space-time is curved so much that it forms basically a bottomless pit. So to kind of understand this, imagine you take a bowling ball, something heavy like a bowling ball, and lay it on top of your nice soft bed. So the bowling ball will dent your bed and pucker or warp the surface of your bed. So the surface up here of your bed represents normal space and time, which is flat. Then straight lines, so if you think of this like a grid of a graph paper. But when you put something heavy on your bed, it bends or warps or puckers the space and also the time around it, because space and time are linked together according to Einstein. So for our sun, for example, the space-time around our sun is warped somewhat. If you look at a white dwarf, since it's a very compact version of a star, the gravity is much stronger on a white dwarf, so the pucker or the warp of space-time is much greater. This would be like putting something maybe like a shot put or something really heavy and dense on top of your bed. A neutron star is even more dense and has stronger gravity, so it warps and bends space and time even more. But a black hole is the ultimate. If you put a black hole on your bed, it basically falls right through the floor and falls to infinity. So this is a bottomless pit, in a sense, in space-time. Now, what this means is that not only is the space severely warped and curved around a black hole like this, but time as well is basically slowed down. So the closer you get to a black hole, the slower time goes. And as you get to the event horizon, an amazing thing happens. Time actually stops. So black holes are sometimes called frozen stars. So these are very odd and mysterious effects that are very difficult to comprehend, because it's nothing like anything we can ever experience here on Earth. We can't actually see black holes because they don't give off any light or radiation. However, as we talked about, we can actually see the accretion disk around the black hole. So the first black hole that was discovered is called Cygnus X1. This is a X-ray, the first X-ray source, that's why it's called X1, that was found in the constellation of Cygnus. And the model for this is probably a black hole, which is shown right here, that is actually devouring its companion. So it turns out that many stars in the galaxy, most of them actually, are binary stars. They have a companion. Our sun is not a binary star. It's a loner star. But most stars actually have companions. So in this case, the companion is a supergiant star. So this is a star that's swollen up to a huge size. And it's because of the strong gravity of its companion here, which is turned into a black hole, it's actually siphoning off material, and it's basically cannibalizing its companion here. Now, this gas that gets superheated and falls into the black hole, this is the accretion disk, and it's so hot, it can be up to 1,000,000 degrees, that it emits a lot of X-rays. So this is an actual X-ray image of Cygnus X1. So basically what we're looking at here are the X-rays of a black hole. This is, as Carl Sagan once said, it's sort of like seeing the footprints in the snow of an invisible man that's walking across the snow. That's sort of what this X-ray image tells us. This is physical evidence for a black hole. Here's another example of a black hole that we can actually see. This particular one is in the constellation Aquila, and it's shown in here in this little square here. That little blip is the black hole, and it's believed to be a 14 solar mass black hole. And this is an X-ray image of the black hole, and it doesn't show up real well here, but there are some faint jets. Depending on how your monitor is set, you may be able to see the jets shooting out of this black hole. But this is an actual X-ray image again of this particular black hole. Here's one more image of a black hole, so you can at least say that you've seen something, or at least seen the footprints of a black hole. This is a 10 solar mass black hole in the constellation of Sagittarius. Again, they think that this is a black hole is basically consuming its companion star here, a giant star. You can see all the gas is being siphoned off and swirling around to its doom as it gets sucked into the black hole, which is right in the center, and then here would be the jets. Now, of course, this is not a photograph or an image. This is an artist's rendering of what is probably going on here based on the model. These are actual images. This is in gamma rays. The black hole is emitting gamma rays, either from these jets or from the accretion disk itself. And here is the same black hole seen through an X-ray telescope. This is the best image we have of a black hole taken to date. This is of a supermassive black hole in the core of galaxy M87. So we'll learn a little more about these supermassive black holes in the next chapter on galaxies. But these supermassive black holes have much, much more mass than a single star that produces them. We actually don't know how these are produced. But this particular one has an estimated mass of 6.5 billion suns. So this is just amazing to think about 6 billion of our suns squeezed together until basically it disappears from space. So this image here, and by the way, what we're seeing here, you can kind of get a sense that the event horizon is somewhere inside of this dark region in the middle here. This is an accretion disk around it of material, and this image was taken using multiple radio telescopes all connected together to get a very high definition and high resolution image of a black hole sitting in the core of a distant galaxy. So this is our last slide here for the chapter on stars. You got to learn how stars are born and formed, and how they evolve and die, and how they produce some of these exotic objects like neutron stars and black holes. Now we will move on to another subject in the next chapter. I will see you then.